welcome to another episode of the Touring Rabbit Holes podcast. Today's is a bonus episode. This is an episode that we originally intended to be one of our very first episodes ever released, and for that reason we have a very formal and a bit longer of an introduction, in which case we explain who we are and why we're doing the show. Now, this episode is a book review episode. We both decided to talk about our favorite science books that we've read of all time. I hope you enjoy this particular episode, and if you would, leave us a comment about your favorite science books. We certainly would love to know. Hi, I'm Gabriel Hesch. I am host of the Breaking Math podcast. Together with Alaniz, we've created a brand new show called the Touring Rabbit Holes podcast to discuss points of view of physicists and mathematicians, such as Alan Turing, who was made famous for building computers that cracked the Nazi Enigma code. We're going to talk about Alan Turing and other physicists and mathematicians and talk about what they might think about today's world. And sometimes on this show, we will do deep dives into math and physics and machine learning and artificial intelligence. We are very, very excited about this opportunity. Now, before I go further, I want to tell you a little bit about myself and why am I part of this math and science show. First of all, I am a former middle school math and science teacher. I am currently an electrical engineer. I got my MS, my Master's of Science in Electrical Engineering. And I'm also currently, as I said earlier, one of the co-hosts of the Breaking Math podcast. It is currently ranked number 1 in the US and Britain on Apple Podcasts for the category of math podcasts. Now, this show's a little different. This is my first time doing a YouTube show, so I'm very excited. On the Breaking Math podcast, I want to mention my co-host is the lovely Sophia Baca, who is brilliant, and we will have her on this show quite often as well. She's quite excited about this show as well. Also, Alex, I'll let you go and talk about yourself and your experience and why you are excited to do a science and math podcast.
Hi, I'm Alex. My background is starting with a master's. I have a master's of science in mathematics, I did non-thesis, which means I did all coursework. Half of it was applied, half of it was pure, so that I could get my PhD in math. I ended up wanting to do something a little more practical than push symbols around. So I ended up getting a PhD in particle physics from the University of Houston back in 2000. I've had some interesting experiences. They're all kind of related. I ended up on a trading floor trading weather derivatives and other energy-based derivatives, learning stochastic calculus, which is adding to my understanding of statistical physics, which then was quite useful when I ended up at Los Alamos as a nuclear weapons physicist. Before that, I was a postdoc at Los Alamos, and I worked on what the United States calls stockpile stewardship, which is the thing that the 3 national nuclear laboratories do to make sure that our nuclear weapons, our stockpile, work. And so I worked at a giant dual X-ray facility looking at implosions and seeing how good we can measure things. And then the guys with the biggest computers on Earth were trying to match that to see if physics code could match that. And I ended up in the physics division facility over there designing. What else have I done?
I'm going to brag on you real quick.
Sure.
Now, in a minute here, this is our first episode. In a little while, we're going to tell you exactly what will be on the Touring Rabbit Holes podcast, why you should watch us, what makes us different from other math and science podcasts. Before I do that, though, I want to say, in addition to the work that you've done in nuclear stockpile stewardship and all the other science and engineering fields, you've also written some fiction books as well, some science fiction books, which we will do some episodes on that are very, very cool, in fact. Want to tell us just a little bit about your inspiration in your science fiction books?
Very briefly, I had the notion back in 2004 that history could repeat itself and there was nothing that made America special, and that what happened to Germany in the 30s could possibly happen to the United States. And I'll defer discussion of that to later, but I would argue that we are in many ways trying to repeat history in that sense. So, and I try to be as historically accurate and scientifically accurate when I get into the future parts. However, what I'm most proud of is my step-by-step notes.
Yeah.
I have written step-by-step notes for your bachelor's, your master's, your PhD in math or physics, because the vast majority of people who get master's or physics degrees walk out with a lot of question marks. I have answered all those questions. I've gone back, say, in quantum mechanics to 1834 and followed everything that led to today's quantum physics. And all these step-by-step notes are available online.
Yeah, that's actually really, really cool. What I find incredible is Alex has shown me this. He has tons and tons of papers. I think some of them are about 45 pages. I think the longer ones are how long? They're huge.
Approaching 200 pages.
Yeah. But what I like is that this is specifically for students who know the answers to the textbook questions in a physics or science class, but they don't know the wider applications, or they don't know, other ways of looking at the big picture. So that's what really excites me about this podcast in general, is all of Alex's papers that he's done that are meant for physics students or people just who are curious about them. All of those papers are available for you. You can look in the video description right now and you will see some links to some Google Drives or some direct links. These are also available on our Patreon page as well. We did make a Touring Rabbit Holes Patreon page for those who want to support us. And all of Alex's papers are on there, and that's really cool. Now, you don't only have papers that are about studying physics and about putting the big picture together. What are some of the other papers that you've published?
So I've gotten into artificial intelligence, say, over 5-6 years, and I've gotten into the deep end of it. I like to read the papers from Google and see if I can duplicate the work myself. I've gotten very much into applications of artificial intelligence in strategic conflict and hacking elections, and how other countries, dictatorships might hack democracies, and how democracies may protect themselves using machine learning and using artificial intelligence for the good and the bad. I mean, Machiavelli has a bad reputation, but he painted, if you want to do A, here's how you do it, and it's black and white. And in that sense, I wrote Machiavellian papers on machine learning and artificial intelligence, and what might be threatening us in the future.
That's a really exciting question. So it's not just the math and science, but we're talking about human behavior. We're talking about defense strategies and things like that. So that's really, really exciting. What I'm also really excited to talk about on this episode are some of my specific interests and where they overlap with Alex's interest, and hopefully the kind of chemistry that will create in order to make a great podcast and really to generate some great questions. I say this later in our episode outline, but please leave us questions and comments in the YouTube videos about the content, and it'll help us to explore these issues even deeper. So what I've prepared for this entry episode is, before we go into some of the papers that Alex has written, I had both Alex and I take a couple of our favorite books in science and prepare a little talk about them and why they're meaningful for us for this episode. This is a little bit like, what's the show? Reading Rainbow with LeVar Burton. I used to watch him all the time on PBS when I was very little. He had a fabulous show where he would introduce his audience to fiction. Well, this segment of the podcast is a little bit similar, but it is nonfiction. It is specifically science and math books, and it's more for adults. So hopefully that is a good analogy with all respects toward Reading Rainbow. Okay, I have 4 books that I brought, and it looks like you also brought 4 books here. So I think I'll go ahead and start with mine here. The first book, by the way, these 4 books have a common theme here. So let's see if we can talk about, or let's see if you can catch what the theme is before I tell you. The first book that I brought is actually a New Scientist instant expert book. You have any opinions on the idea of an instant expert, Alex?
Not possible.
Okay. Yes, it is not possible. But what New Scientist has done is they are a British science journal for the layman, kind of like Popular Science or Scientific American. I'm a big fan of theirs. They spent a long time interviewing experts in certain fields, and they put together a book specifically for the layman. Now, this particular book is called How Your Brain Works. This talks about brain chemistry. This talks about neural circuitry. This talks about how your brain can fool itself. It also talks about chemicals and how your emotions work. And the reason why this is especially an interesting topic for me is my family has some mental illnesses throughout that have forced me to really dive into the literature on what causes mental illnesses and how they're treated. Ones that are especially interesting to me are schizophrenia or a schizoaffective disorder, but also things like bipolar disorder. I'm also fascinated by things like Alzheimer's and what are some ideas to treat them. All of these things deal with the human conscious experience, and for that reason, I'm very curious about how the brain works. So I rely heavily on this, and even though, this won't make me an expert per se, this does provide citations for all of their information, and I can certainly continue on my journey and know where to start. So big influence right here. Okay, now the next book that I want to talk about is a Pulitzer Prize winning book that was published in the late 70s and probably is the most profound book I have ever read. This one is called Gödel, Escher, Bach. This is a huge influence on my thinking right now. If I were to sum up this book briefly, I keep trying to face the mic. I know every time I turn my head, it messes with the audio. Apologies. If I were to sum up this book, I think the author, who was a student of particle physics at the time, I believe he was working on his PhD. By the way, Alex is also a particle physicist. Yay. He tried to think about human consciousness and how to describe it mathematically with ideas such as recursion, as well as something called Gödel's incompleteness theorem, as well as self-reference. It is a brilliant tome. Now, what I also like is that the author, Douglas Hofstadter, part of what influenced him in his thinking was thinking about his little sister, who actually had something wrong with her brain in that she could not understand spoken language. And it got Douglas Hofstadter thinking about language itself and how the brain processes language and meaning. And he wrote down all of his ideas with his mathematics, with his math background. Before I go any further, I thought I'd go ahead and give you the floor, Alex, so you can say your piece about this book.
Yeah, I discovered it because I was interested in understanding Gödel's incompleteness theorem, which we'll discuss later in an episode or episodes on Death of Mathematics. And the idea that there are mathematical systems that are incomplete. There are theorems within them that you don't know if it's going to take an infinite amount of time to prove them mechanically. And so that's why I picked up that book. And I actually read his later book, Le Tombeau de Marot, which is a book on language translation.
I need to read that one. I'm obsessed with language. I should have said that as well. In my Breaking Math podcast, I have like 3 episodes that are all about human language and understanding it, and language and entropy, and language and Shannon's information theory and stuff like that. So
absolutely, he was very much interested. He had the notion that true ability to translate between any two language pairs required human level intelligence, and his whole book kind of argues that, but. Yeah. Maybe he was a little bit off because I think Google's doing a pretty good job, and some of the other translation services are doing a pretty good job.
Yeah, so he can actually be wrong about this. And what's cool is that all of these ideas from these brilliant thinkers that we're presenting, well, they can all be criticized. And, as time passes and we learn more about our intelligence and machine intelligence, they are certainly open to be criticized. So that's pretty cool. Ready for my book number 3? This is an interesting one. Dun, dun, dun. Another New Scientist Instant Expert, Machines That Think. I am very thankful for New Scientist who for the writers of the Instant Expert series, because they put a lot of effort into talking to the experts about these topics. Now, this is a primer on artificial intelligence and neural networks. Now, notice how the first book I mentioned was about the human brain, about chemistry and neurons and information processing and how the brain processes our senses. The second book is an attempt at describing the phenomenon of consciousness from a mathematical standpoint. The third book, of course, is how machines are starting to act more like the human brain. They are not there yet, but they're more like it. I kind of feel like with artificial intelligence, and again, nothing we have is anything like our brain. There's nothing to our knowledge that is self-aware. Is it fair to say artificial intelligence right now is kind of like a complicated lookup table?
Artificial intelligence is many different approaches. So the closest to human brain is trying to imitate biology, and then people they take slices of the brain, they figure out statistically how many dendrites and how they're distributed, and I think people that are trying to make neuromorphic chips that way, maybe you can make a silicon-based AI that way, just basically imitating us. Mm-hmm. Software-based, algorithmic-based, we're nowhere near that yet. Yeah. I mean, if you think about driving a car, I can probably spend 30 seconds and show you that it's no big deal. You literally say you put a camera on a car in the middle of a road, and if you drift to the left, in post-process, you put an arrow that says proportional go to the center. If you start drifting that way, you put an arrow that way, say go to that way, and then you have a car that drives. It's like it looks like it's behaving intelligently, but it is not intelligent, and so we have to worry. We're in the intelligent behavior age, not intelligence yet.
And what fascinates me is this. this is not meant to scare any of our viewers. I want to offer you a criticism of artificial intelligence and neural networks. We know that if you make something that computes things like, say, an abacus, nobody that I know of would describe an abacus as intelligent, at least in the way we commonly think of it. If you add some more machinery and complexity to an abacus, like something like a 1700s Babbage engine, for those of you who don't know, if you haven't looked it up, the Babbage engine was a rudimentary calculator that involved cranks. It's kind of like a steam-powered, like a steampunk attempt at a calculator. It was never actually made, but it was designed. Anyways, all that to say, it's still just machinery. So as you add more complex machinery and more algorithms, does that at all ever mean that something is intelligent? Well, it's hard for me to say yes to that question. At the same time, what are we, if not a combination of machinery and neural circuitry and algorithms? That's a great question.
Well, yeah, that's a very good point. I mean, yeah, we are quantum mechanical devices that compute. My approach is one of entropy reduction, and I was thinking, if you say we could go into a museum and have a hologram of Einstein, and how would we talk to him? And how does one make an avatar that's smart? And chatbots they're pseudo smart. You might grab, say, the glossary of a big science encyclopedia, and you'll load that as a text file. And what machine learning for natural language does is it allows you to type in, I'm interested in binary stars, and it goes and digs up things on binary stars, and you think, this is an intelligent thing. And you might have a foreigner typing, you might have a child typing, you might have different people typing, and it's pretty good at doing that. So you think there's an intelligence there. But what it's really doing is it's taking the 20,000 words that are in the glossary and literally making a vector space of them so that the word star is the 7th entry, the word binary is the 108th entry. And when you type, it vectorizes your sentence against the vector space of sentences, and it goes dot product, dot product, dot product. Oh, that's the one.
Yeah. So in short, I mean, really, it's just a machine. It's still just a machine, and I want that to be, a driving critical, a way of criticizing the fear of artificial intelligence. That's not saying it can't happen. The assumption, if you go under the belief that we are mechanical beings ourselves, then it theoretically is possible. But
so what I wanted to add to that was, if you just put that text file in, you have a gigantic entropy. There's no connection between the sentences. So what I've been doing is chopping it up into smaller text files, and then I put what I called probabilistic DNA. If I said this, then I might say that as an expert. Oh, and by the way, I might jump to this file that's related. Oh, if you're interested in binary stars, are you interested in binary stars like that are black holes that collide and we can detect them with gravitational wave telescopes? And so looking at that, we have graphed ourselves. Wikipedia is the graph of us. That's just the graph. What are the rules? How do graphs evolve? How do countries evolve? How do people evolve? I think once we get to do that, and we use entropy reduction methods, algebraic topology, we will start to see scary, possibly not conscious, but scary AI.
Yeah. And actually, before we began recording this episode, I was talking to Alex about a researcher that I follow on Twitter. Eulers Gem, actually, he is the author of a fan fiction version of Harry Potter called Harry Potter and the Methods of Rationality. And if I mispronounced his name, my apologies. Actually, I'm going to look it up while I'm here, make sure I get the name pronunciation correctly. Sometimes I read things so fast that I don't take the time to read it out loud in my head here. But Eulers, here we go. Yeah, I think I have it right. Eulers Gem. His middle name is Shlomo, actually. So he has this idea of friendly artificial intelligence. He's not afraid of artificial intelligence. He believes it will be benevolent. Well, there's a lot more to it, and I want to be fair to his opinions. And Alex does not share that opinion. So I think an interesting possible episode would be, is artificial intelligence eventually something that we should be afraid? Why or why not? And we will look at papers by Eulers Gem as well as.
I think it's too easy for nation states to try to use machine learning and artificial intelligence to hack each other, to hack each other politically, to be divisive, et cetera.
Yeah.
Certainly the Department of Defense is looking at autonomous weapons, and so that's not very friendly to me. It doesn't sound like you'd want to shake hands with some of these toys.
Yeah, fair enough. So there's a lot to say on those topics. So hopefully this will sell you on why you should subscribe to this podcast right now. That's my goal. We want to have really great conversations about the deep questions. And of course, so far we have how the human brain works, and then we have machines that think, and how are they similar and different. It's kind of like we're approaching consciousness like through the method of exhaustion that Archimedes used to approximate pi, where you get closer and closer and closer. Now, I have one more book, actually. This last book is not specifically about the human mind. It is not about artificial intelligence at all. This book is actually the book that inspired me to make a podcast in the first place. This book is called A Quantum Story, A History in 40 Moments by Jim Baggett. Fabulous book. I actually talked about this book as it's a thick read. How many pages is it now? It's 400, a lot more than that. It's, oh gosh, your notes are all over this page, Alex. Don't you love it when you pick up a friend's book and they're filled with notes? Alex's is filled with notes and diagrams. Hope you don't mind me showing that off. This book essentially is a history of quantum mechanics, starting with Max Planck and his discovery of what is now known as the Planck length, which ushered in quantum mechanics. It then gets into fierce debates between Albert Einstein and Niels Bohr about the nature of quantum mechanics, and is reality something that is fixed, or does it change when you observe it? And that's only in the first third of the book. It then gets into Richard Feynman and Feynman diagrams and the standard model of physics. It goes all the way through. I think it ends out talking about some ideas both in string theory and theories that compete with string theory, such as quantum loop gravity. It's a thick read, and I actually introduced this as the Texas Steak Challenge, because I know there's restaurants, not only in Texas, I just, use that name. There's many restaurants where there's a steak challenge where you have to eat the whole thing, and if you eat the whole thing in a certain amount of time, the meal is free. This is kind of like it. If you can read this whole thing in, I don't know, what would you say a fair time is? A month? I mean, it depends on your background.
Yeah, right. Let's say a month.
Okay, a month. Yeah. So I want to talk to the author, Jim Baggett, and say I talk about your book as the Texas, or as the physics reading steak challenge. How's that? Those are my 4 books. Those are the 4 that I have. That's all I have to say about those issues. In this podcast, we'll be talking about ideas.
So keep that book there.
Yes. Okay.
Our previous employer was the Air Force Nuclear Weapons Center. That's where we met.
Yeah.
And we had these kinds of chats that we're talking about right now. And he asked me to read this book, and I was dismissive because I have studied the hell out of history of physics and math. And I have to say, I learned. It was very interesting to see the debate between Einstein and Bohr that runs through a large chunk of the book on, what is quantum mechanics, that we need to replace it with something else because of the spookiness of it, right? Because of teleportation, the Einstein-Podolsky-Rosen paradox. So I stand corrected. It's a fantastic book to read.
I'm glad to hear that. That makes me feel good. And not everything I read is deep. I read all kinds of simple, I don't want to judge a person by the complex books that they read or whatever. This is a complex book. It is, it's very complex, but it's a wonderful read. Oh my gosh. Without further ado, I want to hear, Alex, about what books you brought to talk about.
So my relation with books is the following. I think when I moved from Los Alamos to Albuquerque to come work for the Air Force, I probably threw away 3,000 or 4,000 pounds of books. I'm a minimalist. I have a library back there. Mm-hmm. I want to get to the minimalist representation of physics and mathematics, and later on we'll get into how fiber bundles wrap up general relativity and standard model and let us explore potential universes in a very concise way. This is a book I ran into when I was in grad school. It was in a different edition. This is in second edition. It's Quantum Field Theory by Ryder. And what I really like about it are the first 2 chapters. Skip chapter 1, go to 2 and 3. It shows how we got to the standard model. Paul Adrien Maurice Dirac derived an equation for electrons that was relativistic and quantum mechanical. And if you have a special relativity equation, you should be able to transform it into Lorentz transforms, which are the transforms of special relativity as opposed to Galilean in classical mechanics. And he got crap out of it. He got his equation back and some crap. So he starts wiggling around, putting in terms, and eventually, putting in terms, transforming. And when he finished, and what he started on the left equals what started out, what ends up on the right was Maxwell's equations. He had to have Maxwell's equations for a relativistic theory of electrons. Quantum mechanics uses the complex numbers, and if you think about the complex numbers, the number 1 is a magnitude, is a length. So everything along a unit circle has length 1, but if I don't tell you the angle, you don't really know. So wave functions are complex. Measurements in physics are the magnitude, is the wave times its complex conjugate, and square root, and you get the measurement. So the group of the circle is the group of electrodynamics, U1 group theory. So people went to the next group theory, and they developed an equation for the weak force. And it has SU2 is that group as opposed to U1, and it has 3 parameters. And those are the 3 particles of the weak nuclear force. Then they went up to SU3, a deeper, higher dimensional group corresponding to a higher dimensional hypersphere, and they were able to identify the 8 gluons that way. And so there's this idea that we have this carte blanche. We'll look at SU5, which is a bigger theory, and it says that protons should decay, and we go and put protons in a swimming pool because the proton's water. And we look for decays, they don't happen, so we throw away SU5 and we go on to other groups. The converse of that book is this book, which is not an easy read, and I battle it for years. I have written a step-by-step set of notes online that will teach you the homology theory, the homotopy theory, the cohomology theory, to get you to read, to get to chapter 7 in this book, which finally shows that all theories from general relativity, where the group is Lorentz transformations, versus particle physics, where the groups are symmetry groups, can be compactified in algebraic topology of fiber bundles. And so these are this and supposedly this book right here by Nakahara I hated these books. I've battled them for years and years, and finally, I started to get them to make the breakthroughs. I found that several physicists a couple of them wrote a paper on how to read the book by, I'm sorry, I don't think I identified the authors, Nash and Sen, Topology and Geometry for Physicists. There's a paper out there that helps you read this. Well, having written the step-by-step notes for this book, that paper actually helps too. But I'm going to write a paper for that paper.
Sorry, write a paper for the paper, and I'm going to write a paper for the paper for the paper.
No, because it's too abbreviated. They use machinery that they don't elaborate on. So at some point this year, I will have this completed. Right now, it's pretty decent.
Here's what I love on this podcast, just real quick. What I love about this is that I have these 4 books, and I'm saying, yes, you need to read it. And then Alex has 4 books. He's like, don't read these are monsters. Oh, my goodness. But what's amazing is that following those books, Alex wrote a paper, so you can read his. I mean, I'm not trying to say don't go out and buy that book, but you have a summary. A lot of those books have influenced your papers that our audience can read right now.
Literally, if you've had maybe a semester calculus, but preferably an undergrad in math or physics, I build it step by step.
Okay.
So there's no mystery. There's no, where did he pull this from? None of that.
Yeah.
And if you read that, you'll have a good understanding of this. You won't have a perfect understanding of chapter 7. The paper that I found by the 2 physicists on it helps. Okay. So I'm going to make it perfect.
Yeah, nice. I wonder if they want to be on our podcast ever. We should ask them. It never hurts to ask. And then wait a minute, you have a book there as well. If I'm seeing it correctly, a book on Euler. Is that right?
Well, and it is related to everything we've been talking about. Euler's Gem. He discovered a formula which lets you tell the difference between a donut and a cup of coffee. Say a cup of coffee, you can deform it into a sphere.
I've always wanted to know, how do you tell the difference?
Vertices minus edges plus faces equals 2 for a sphere. So if you think about a clay tetrahedron solid, you can rearrange it into a ball. But if you rearrange it back into a tetrahedron, you count the vertices, the edges, the faces, you v minus e plus f, you get 2. If you put a hole in it, a donut, and then you pixelate it, say you turn it into having faces and edges and vertices, and you do that formula, however many vertices and edges you want, the simplest, as complicated as you want, and you do that formula, you'll get 0.
Okay.
So one is 0 and the other one is 2. That is a deep result coming from homology and homotopy theory. That's the foundation to fiber bundle theory. But this book is actually for the general readers, and it shows you combinatorial proof. Everyone thinks of math as calculus on a board. Yeah. There's algebra, as in group theories. There's geometrical methods. There's combinatorial mathematics, and that's one of the things I'd like to discuss is the other types of math that people generally don't think about.
If you're talking about that, suddenly I'm wondering if for our marketing, for our merchandise, can we do like a geometry and topology coloring book?
Sure.
I'd like that.
How many colors do you need to not have
4-color theorem?
Yeah.
I'd be interested in a quantum physics coloring book. I really would be. I think that'll be my contribution.
Okay, awesome.
Cool, very good. Okay, before we start the wrap up of this episode, I want to say one more thing. I'm excited to announce on this podcast, and actually I've already alluded to it in this conversation already, is that we have a Google Drive that is filled with papers of topics that interest us. Stuff mostly Alex has written. I'm writing a few. They will be in the drive shortly. The topics include black holes. They include the fundamental limits of mathematics and human knowledge itself. They include things like how machine learning might be used in warfare. Also, how fake news spreads like a virus. You can read these papers right now, and they are not over-the-top complex. They are kind of like the conversation I'm having right now. There's not too many equations. Well, in most of them. Some of them do deep dive into the mathematics. But look in the description of this video, and you'll see a link to some of the papers. Let's just talk. I mean, there's a lot of papers right now, but I think for the sake of this video, let's only talk about a couple of them. The first paper that we have is from Alex, and you alluded to it. It's Algebraic Topology and Fiber Bundle Physics. Can you give us the Reader's Digest, a couple sentences on what that's about?
I think effectively I did that. It builds a more general vector calculus. It's very step by step to understand how physicists can create a new universe. That makes it sound maybe too simple. But it is, in a way, very simple to think about other kinds of universes versus more down-to-earth things like the physics of turbulence, or the physics of what's going on inside of stars with turbulent dynamics. There's a lot of things that are complex because a lot of complexity happens in them. But if you're thinking about designing universes, then this is a very good way to do that.
Very cool.
So it's essentially what we were talking about, the summary of the books.
Very good. Yeah, and then there's also one that's not quite as math heavy that we are actually talking about very soon, maybe in our next episode. We shall see. There's one called The Doctrine for and a Path to Warfare for Artificial Intelligence. That one is, it's a fabulous read. That's literally about how fake news is used by countries as a form of both defense and offense. It's fabulous.
So thinkers, when the airplane got invented and was used in World War I, people began to make doctrine for air power. And it took a long time, decades, before their visions were actually realized. I mean, World War II, it took a lot of bombs to have the effect they were looking for versus a single laser-guided weapon today. So it took a long time, but we should be thinking about doctrine. And I work for the Air Force, and I'm hopefully going to be developing didactic material for the Air Force at some point, trying to make people wake up that we need doctrine between nation states for these technologies that are coming. Mm-hmm.
Absolutely. Then that's a fascinating one. Obviously, that's in sci-fi all the time. The Terminator series, where you talk about Skynet, that's a huge thing. So obviously, science fiction authors have been thinking about that for a very long time. And I'm not just talking about Skynet, of course, but this is just, in general, we need a doctrine for information, for machine learning. So that's a fabulous paper. The third paper that I'd like to talk about is one of them called Mathematical and Physical Limits for Mortals and Immortals. I love the title of that. So if you don't mind, so the book is... It's kind of about the death of mathematics, starting with Gödel's incompleteness theorem, but and that's a big part of the book Gödel, Escher, Bach that we talked about before. But I wanted to ask you about the title. It's the Mathematical and Physical Limits for Mortals and Immortals. Why did you pick that title?
Because if you are an intelligent being and you are using symbolic logic of some kind, and it is sufficiently rich that it is sufficiently as complex as, say, the integers under the normal operations of addition, subtraction, multiplication, etc. If it's at least that sophisticated, you already have Gödel's incompleteness. You have theorems that may be true, may not be true. And let's back that up. The program was in the early 1900s. David Hilbert wanted to ask, is there a way we can create mathematics so clearly with logic and symbols that we can create mechanical means of proving a theorem? Your computer is the best example of that. You may be writing your favorite, the best scene of your life on your novel, and your computer freezes. And the computer is an object operating on ones and zeros, arithmetically, purely logically, and you don't know how long you're going to have to wait. Might you have to wait infinity? Might you have to wait 2 minutes? That is the essence of the Gödel incompleteness theorem, and there are many more other things. There's in the 1960s, it was shown that we can't even guarantee consistency. Say you're a ninth grader and you're going to be stuck around for 1,000 years proving theorems. You might eventually get to 2 theorems that you've proved, and they're all logical, but yet themselves contradict. You can't even guarantee from consistency. That's a bound for gods. That's a bound for mortals.
Got it. I like that. I like that. That's a powerful statement. Very powerful statement. The last one, and then we'll wrap this episode up as an intro episode. The last one I thought was really cool. This last paper that will be in the links for today's episode is a reflection on the PBS Spacetime series on black holes. That is one of my favorite YouTube series of all time. Same with Alex. So yes. You watched every single episode of the PBS Spacetime show that was on black holes. Is that right?
Correct, and the more you know, the better the show is, and I find it as a really good organizing tool. So I actually made a lot of notes to make a paper, so that you could read a step-by-step notes and have references to his podcast.
Yeah, that's very cool. It's kind of an accompaniment. So we're big fans of the show. So maybe someday he'll see.
So that episode ends with conformal field theory, holography. There is a way that you can have an interior, a 4-dimensional interior that has quantum physics and particle physics, and on the edge, the boundary, which is 4-dimensional, you have a theory of gravity. If you can just go one less, so from 3 dimensions in the guts in the body and 4-dimensional boundary, then we would have solved quantum physics and the unification with gravity. And so I thought that we're that close, but it may not ever get there, but that's what the episode series is about that I wrote the paper about.
That's exciting. I think about, there are limits that we will never reach, but we don't know what those limits are. And
there are workarounds. That's another discussion we can have.
Yeah, that's cool. Alrighty, so that's probably enough for one episode. That is quite a deep dive. I actually intended to keep inserting the pun. Wow, we went down a rabbit hole, didn't we? And then stare at the camera oh, just kidding. I won't do that. I promise. Yes. I won't do that. But yeah, there's a lot of rabbit holes. So all those papers are available if you really want to dive deep in the Google Drive that is in the video descriptions or in the show notes. Now, I guess as we wrap up, we want to say that we really would love to hear from you. If you have a question for either myself or for Alex or about the papers, send us a question in the comment section. If you don't want to comment in that section, you can also send us a private email at touringrabbitholespodcast@gmail.com, and both Alex and myself will get them. And if it's a question for Alex and I get it, I will forward it to you, and vice versa. So we will be happy to answer your questions. Now, the best way to support the show right now, I'm hoping that you've enjoyed this show, and if you like the podcast, if you like the video, and if you subscribe to us right now, that is probably the best way to support. We also do have a Patreon account as well. If you go to patreon.com/touringrabbitholes, again, that's patreon.com/touringrabbitholes. We currently have a tier, a $5 tier, which I have called the Higgs boson tier. We have a $10 tier, and I'm forgetting what I did that one, maybe Incomplete or Event Horizon, I think. I don't remember.
I don't recall.
There's a $10 tier, and also there'll be higher tiers, like a $20 and a $30 a month tier. That helps us a lot. What we intend to do with our Patreon donations is we'd like to hire local creative people. We want to hire people who can edit videos or learn to edit videos if they'd like to intern. We'd like to do a paid internship. We'd like to hire people to make graphics in any sort of graphical software at all. We'd like to hire people to work with marketing. We'd love to get creative people involved with science, technology, and engineering, STEM people, for lack of a better word, who want to make great content. That's literally what we want to do. So the Patreon is the best way I can think of to do that. It'll help us to actually pay our interns. That would be really appreciated. So please consider becoming a patron, or again, if you like the show, please share it with your friends. We would greatly appreciate that. Any plugs or anything else you'd like to say at this time, Alex?
No, I just want to thank you because this is his idea and he has the background, so thank you.
Oh, absolutely. Okay, my background is from podcasting previously, so I just love these conversations, and I love having them with Alex, and I want to share them with the world. So hopefully that's a whole lot of enthusiasm. So without further ado, by the way, look for bonus episodes. We're going to have bonus episodes that are our planning episodes where we're just chit-chatting back and forth about crazy papers, and maybe Alex has to clarify something for me. Those will be really cool. Those may be a Patreon-only thing. Keep a lookout for those.